of Chapter 2 is derivatives. I wanted to make sure that you guys had super solid the foundation of differentiation, which was what you just took the test on. Okay? But there were a couple extra things in Chapter 2A really quickly. Extra things would include motion. That was extra beyond the foundation. It is foundational, but it's not foundational to just solving derivatives. It's foundational to applications. Motion was a little bit extra. And I think the hardest topic of Chapter 2A was chain rule. And that's assuming that you memorize your Forever cards. How many of you guys at this point, after finishing the test, are still kind of like, I'm not yet completely solid on my Forever card rules? Okay, yeah, probably about half. So you just need to keep studying. Some of you guys are like, no, it's coming like clockwork. Good, but those of you that it's not coming like clockwork, you just need to keep drilling those rules, okay? The trig ones, even the chain rule, the product rule, the quotient rule. Keep drilling them. Have your Forever cards close when you're doing homework. You're just reinforcing in your brain, these are the rules, this is what I need to know. And if you have your Forevers you're studying from, it's something consistent, and consistency is good. Kiddos, what have I done? I was going to say, it just kind of came out with it. I don't know what have I done so far in trying to find dy dx given this function? What's weird about the function to begin with? Yeah, the x, well, the x's and the y's are all kind of mixed, right? So how do I start rewriting? What am I doing?
Isolating y alone.
Isolating y, getting y alone. Right, just moving things around, right? Once I get y alone, it's time to take a derivative. Did anybody rewrite it one step further? No one rewrote it? You guys just went quotient rule?
Yeah.
Okay, totally fine. You could have also done the heart method. You guys remember the heart method? You could have divided each of these. You could have divided this one by x and that one by x. You would have had -3 plus 10 over x. Some of you might like taking that derivative instead. But let's go ahead and just use the quotient rule. That's what you guys thought. Hopefully some of you were able to already do the quotient rule, so let me go ahead and get into it. So we have bottom d top. D top, you guys got -3, right?
Mm-hmm.
Plus 0. The 10 derivative is 0. Minus top d bottom, -3x plus 10. Derivative of x was just 1. All over? Bottom square. Good. Okay. Now when we go to simplify, make sure that you are very careful with that negative, right? With that subtraction. But we have -3x plus 3x, true? Minus 10 all over x squared. So we end up with our final derivative being -10 over x squared. Okay, do you guys agree? Cool. Can you look at the other variation up here? Would that have worked out the exact same if we had rewritten first and then derived? What's the derivative of -3? 0. How would I have taken a derivative of 10 over x? Quotient rule maybe, but can't you rewrite that one too? Yeah, you could have written it 10x to the -1. Couldn't you have brought down the -1, -10, x to the -2? Works both ways. Was this one possible? This mixed up function, we technically call it an implicitly defined function. That was from pre-cal, but it was a long time ago. Implicitly defined means the x's and y's are all mixed in, y is not isolated. An implicitly defined function. Could we take the derivative just by rewriting and using the old-fashioned rules? Last chapter, not super old-fashioned, but that's okay. These days, don't things become like outdated within like a few days or like a month? It works. Okay, so the old-fashioned rules from last chapter, yes. But what's the dilemma at the bottom of the page, guys?
If you get like some weird square roots and whatnot in a giant mixed up function, it'd be very hard to isolate the y.
Yeah, what if it's super hard to isolate the y? This one they isolated pretty nicely, but what if it gets more difficult? Like this one. I want you guys to think about what if you did try to isolate the y. What if you did try to isolate the y in this one? Could you get y totally alone?
Yeah, you could.
How?
Divide by, subtract the 5x.
Okay. If I were you, I wouldn't write this down, by the way, but if you want, I'll try it, and then if it works, you'll write it down. I love that. Okay, so we'll subtract the 5x. We have y squared minus 3xy equals 10 minus 5x, or -5x plus 10. What else?
Yeah, you can pull y out. Oh, shoot. And with, yeah, you can't really go with
You guys want to see how we, or I would probably try it? I would probably try. Anybody know what I'm about to do?
What, are you gonna complete that square?
Yeah, I am. So I can take the coefficient of 3x and divide it by 2, which would be -3 halves x. Then I'm going to square it when I come back up here, so that'd be 9/4 x squared.
Yeah.
And then I would go ahead and add that to the other side. Then what would I do? Then what would I do? Okay. Long story short, might this one have been somewhat possible? Yes. But wouldn't it be super nice? Wouldn't it be super nice to have another way? And if you're like, well, but you were able to, okay, fine. What if I was to make that a cube? Now we're in trouble. Now who knows what we're going to do. Okay, so if that was a cube or a fourth or a fifth, or if there was a square root of y in there somewhere, our complete the square only works with a y squared and a single y. So we'd be in trouble if anything got any harder. Now, I want you guys, before we answer this question, how many of you guys already wrote this in your notes? Only one? Okay. You can see how many lines to skip. Skip for me. Those of you that already wrote it, skip like 4 lines. Or if you have an eraser, just already said that works too. Another way of looking at it, we're going to come back to that example in just a second. I should have warned you and I apologize. You could skip 4 lines and we'll come back to it because that's going to be our example in just a second. But first of all, in order to talk about implicit differentiation, which is the idea of taking an implicitly defined function, aka a mixed up function with x's and y's all over the place. Y is not isolated, y is not alone, and taking the derivative. Before we get back to that example we were just talking about, I want you guys to think about the question, why do we write, or when do we write dy dx? When we have a y and we're taking examples. dy dx comes from taking d dx of a y. Now up until this point you've had like sections where it said find f prime of x, find the first derivative, find dy dx. Take the derivative, derive. And so some of you just got into the habit of writing dy dx or f prime of x, which they're similar, they're synonymous. Just the notations are a little different. Of writing dy dx equals and then the answer to the derivative. But why do you write dy dx? Because you're taking the derivative of y. And when you take the derivative of y, think about it this way. Think about the y as a u. And the u prime is dy dx. And so if we were to take the derivative of u, it would just be 1. And the derivative of y would be dy dx. Now, how is this different from taking the derivative of x? What happens when you take the derivative of x, guys?
So they cancel?
Yeah, the derivative of x is 1. And if I was to take x prime, it would technically be d dx of x, which would be dx dx. We just never write it because what is that in essence? 1. So the derivative of x is just 1, but the derivative of y is 1 times dy dx, which is why we write that as being left over. So if we can take the derivative of y himself, we can take the derivative of y squared, or x times y, or square root of y. We just need to remember that when we're taking d dx out of an expression of some expression in terms of y, we have to have a u prime, which will really be a y prime at the end. When we're taking the derivative of y, We're going to take the derivative just as though it was x, but we have to have a u prime at the end. Thinking about it as chain rule might help just a little bit in that. So if we were to come back, oh, that's the example we did at the beginning of class. Okay, hold on, pause. Let's go ahead and derive it the new way. This is the one I was able to get y by itself, and we just solved a second ago. That is one way of solving this one, but the new way of solving it uses implicit differentiation. It says, hey, take the function as it is, and just say, I need to derive both sides. In a sense, thinking of it algebraically, what you do to one side, you do to the other. I need to derive both sides. So what if we didn't get y by itself? We're building up to that crazy one. We're getting y by itself is super hard. Or other ones, we're getting y by itself is impossible. We're building up to that. How would we take the derivative of 10? That's the easy one, guys. Good. So the derivative on the right-hand side would just be 0. Okay, left-hand side. How do we take the derivative of 3x? And technically times x prime. If you were to say use x, which is just 1. How do we take the derivative of x times y? What rule do I use? Product rule, because it's x times y. Because it's x times y. Okay, product rule. Give me the chance. What is it?
Second d first.
Second d first plus first d second. So second is the y, right? Just rewrite it. D first. What's the derivative of x? 1. Plus first d second. Question. What's the derivative of y? Derivative of y is? Y dx. Or you could say y prime if you would like. You're allowed to say y prime. Some people do. So second d first. Why did I not write a dy dx earlier? Because I was just rewriting the y. No big deal. Second d first. Plus first d second. Ooh, but when I went to go take the derivative of y, I had to put a dy dx. Now, how would I solve for the derivative? Now. Move everything. Yeah, just get dy dx by itself. Tyler, go ahead.
This might be flawed mathematically, but do the x and the d dx cancel? Like, does the x multiply in, or no?
Do you mean dx?
No, x times dy dx.
Oh, no. The dx is grouped. It's not d times x, it's dx, the differential of x. So it's a completely different term, kind of like delta x is different than x. Sorry, do you want that? Oh, let's go ahead and move stuff, yeah? So what can we move? The 3. We can subtract 3 to the other side. And what else can we move? The y, right? We subtract the 3, we can subtract the y times 1 is just y. Then we have x dy dx equals negative 3 minus y. Last step is just divide both sides by. Now here's where it gets a little bit weird. If you don't get y alone in the beginning, you are going to, when you implicitly derive, you are going to end up almost always with a derivative that is also implicit. What is that? A derivative that's in terms of x's and y also. Now, look at the very beginning of the example that we did at the beginning of class. Did that derivative have x's and y's? Why? Because we got y by itself. So all of our function was in terms of x, so our derivative was in terms of x. So is that answer from the beginning, negative 10 over x squared, going to match this one that has y's and x's in it? It's not going to look the same. But how can we see if it actually is the same? Sometimes, wait, pause, sorry, before I have you do that. I don't want you to think what we're about to do can always happen. It can happen in easier functions, or it can happen in really tricky ones, but it's not going to happen in the in-between. It's going to happen in really easy ones, or it's going to happen in more tricky ones, but not the in-between. They're just kind of normal implicit. What we're about to do is say, how can we get this to match that? We ask ourselves the question, can we plug in? We're asking ourselves the question, can we plug in to simplify? Well, plug in what? Well, I don't know, anything. Can we solve for x and plug in? I don't think that's a good idea. Can we solve for negative 3 minus y? I don't think that's a good idea. Can we solve for negative y? Well, we can solve for y. Didn't we solve for y a second ago?
Yeah.
What did we figure out that y equals?
Plus.
All over x? Negative 3x plus 10 over x. So if we wanted to, which in this one, guys, it'd be kind of silly because you're just making it a little bit more complicated, but if all the multiple choice questions had derivatives only in terms of x, you would need to figure out, oh, there must be something I can do to substitute to plug in. And so if we were to plug in and simplify, we would have negative 3 minus negative 3x plus 10 all over x all over x. I'm going to go ahead and distribute that negative because that's just weird eating out right now. Then I would multiply top and bottom by x. So I plugged this into the y spot. I distributed my negative because it was messy. When I multiplied by x, I get negative 3x. I distribute in, x's cancel. And x times x is x squared. Does it end up being the same thing? And the answer is yes, but it sure wasn't fun to get there. If you can get y by itself, that is a really good idea to do. If you can get y by itself, it's a good thing to do. But implicit differentiation, the whole point is what if you can't get y by itself? Now, this got messy really quickly, but the question is, can we actually take derivatives even if y is not alone? So, can I go back to that example that we skipped a second ago? And can you guys try? And I'll start you off. This one, it was super hard to get y by itself. So if you didn't write the example, now's a good time to write it. I'm not going to do the whole thing, but I am going to start you off. The derivative of y squared, think of it as u squared. It'd be 2u. But I need a u prime, which is going to be y prime, which you could write y prime or dy dx. I tend to not write y prime because it starts to look kind of confusing. The y's and the y prime starts to look alike. Some people do it my way with dy dx, some people do it with y prime. Yes. And if you skipped product rule, oh, it would have gone horribly wrong. Alright. I'm going to keep passing out notes, so you guys try to get ahead of me. You guys try to get ahead of me. This is our last example. Check before you start simplifying if you always matches. Weird. Lots of it. But where's my dy dx? 2 places. Well, how? Wait. We're going to top brushing or write down steps tomorrow that you want to get the dy dx terms alone. So move away anyone without or any term without a dy dx, which is why I'm going to add the 3y to the other side and subtract the 5. And move away every term without a dy dx. Because if I can get all the dy dx terms on one side, guys, you were right there at the answer if you just factor, right? Pull out the dy dx. The last step is to struggle, divide. Now, every now and then, there is something that matches up from the original that you can plug in to simplify, but more often than not, we just leave it. And if they did want us to find a specific derivative, they would need to give us an x and a y to plug in. Late Apple Kids homework is online, so if you think you'll have time tonight, come get your spirals by the end of the day. Anything graded will be on the front table. But otherwise, you can grab your spirals tomorrow. 0 period if you want, and we can work on homework in class. Section 2.5. Oh, on to Lisa. I just thought this was that way you can just take your time and throw in headphones or whatever and just be everything. Does that sound good? Yeah. Anything else I can do with me? Okay. Thanks, Miss. Who's this? Zach. Zach.
I'm leaving, I swear. I don't want to stay for pre-chem.
No?
I had enough of that class.
I know, you were bored in there.
It was impossible.